Hello, my dear students. In this series, we are going to talk about very important topic, which is very, it is very useful for this current scenario, which is called physics informed neural networks, right? So, if you try to find out material on these physics informed neural networks on internet, you will see that there is a very limited amount of material or information available regarding these pins. So we will be, what we will be doing in this particular series, we will try to cover every part, starting from like every detail, from very basics, like what exactly we are trying to achieve in this particular course here on physics informed neural networks. And we will see that they are very useful as far as solving the physical systems, right, concerned with the help of machine learning. So we will see that this is, meeting of the physics, older physics we know, and the neural networks right now, they are the talk of the town. So we will see that these two famous topics are meeting together to give us something which is physics informed neural networks. But in this today's video, which is the first video for this particular introduction, what we will look at is what happens to our predictions of neural networks when the data is noisy. So we will be looking at an example, and then we will try to combine everything, and we will see that what exactly, how exactly the things are going for pins, right. So let me give you very basic examples and very basic things which you already know, right. To what I'm trying to do in this first video is I'm trying to set the ground, right, for pins to come out. So let me ask you a question. Let's suppose you have a car, right. Suppose this is a car and the weight of the car is 200 kg, and you are applying a force of 2000 Newton, and the car is asking, what is my acceleration? What will be my acceleration? Right? So, what answer are you going to give to this particular car? So, we already know that Newton, Sir Newton, Isaac Newton will come for the rescue, and he will say that you can use my laws, you can use my second law of motion. So, he will say, hey, use my second law of motion to answer the car. So, now if I ask you what is the second law of motion? So, the second law of motion says mass into acceleration is equal to the force applied. So, here mass is 200 kg, acceleration is what we are looking for, and the force is 2000 Newton. So, the acceleration would be 2000 Newton divided by 200 kg, that would be 10 meter per second square, right. So, this is pretty simple. So, when you have a physical system, and we already know that this is governed by Newton's second law of motion, right. So, you can straight away give answer to your car that okay, this is your acceleration, right. It's very simple. This is what we are doing for many years, like almost a century. This is what we are doing, right. From your class 9th, 10th, 11th, 12th physics, you are using all the Newton's law of motion. Okay, now let us go to another world where we do not know anything about Newton's second law of motion. Suppose we are in a world, we are in a world where Newton's second law of motion is unknown to us. Newton's second law of motion is unknown to us. So, what to do there? In that case, what you can do? The neural networks will come into picture. The neural networks will come into pictures. They look something like this, right. So, they are networks, right. Neural networks, or you can say machine learning or AI, will come forward and will try to help us. So, but they will say, the neural networks will say, we can help you in finding the acceleration, in finding the acceleration, but we need a data set. But we need a data set to learn from, right? So, you will say, okay, that is fair enough, but then you will think how we can collect our data. Then you can maybe ask somebody to do some kind of experiments, right? So, what you can do is you can do some experiments. So, for that you will be needing, because you want a data set for force and acceleration. So, measuring the force is done by force gauge. So, you will have an instrument like this, right? This is something like this, an instrument which is called force gauge, which will measure the force acting on the car, and then acceleration you can measure using accelerometer. Right. So, suppose what you are doing is you are making masses fixed 200 kg, and then you are calculating your acceleration, right, in meter per second square using your accelerometer, and then you have force in newtons using your force gauge, right. So, suppose you calculate this, the experiment is done and you calculate this, that for 1750 Newton force the acceleration comes out to be 8.75, and then for 2902, when this is the entry in the force gauge, 14.51 is the entry in my accelerometer. You can actually do these kind of experiments, right? When there is a force of 2464 Newton, and then at that time 12.32 is the acceleration in my accelerometer, and when the force is 2198, the acceleration is 10.99. When the force is 1312, then the acceleration is 6.56. When the force is 1116, then the acceleration is 5.58. When the force is 2732, the acceleration is 13.66. This is the data which I have actually generated. When the force is 2202, in that case your data acceleration is 11.01, and when the force is 2416, the acceleration is 2.08. This exercise may seem mundane to you, but sometimes we just looking at the data set, we don't get much of the information, we don't get the feel. So, it is a good idea when you are starting a topic that you do it very calmly, starting from every point, right. That gives you a stand of like a sense of holding, right. Then you can go for bigger data set where you cannot write each entry, right. And everywhere the mass of the car is fixed 200 kg, right. So, now if you see how many data points I have collected, 1, 2, 3, 4, 5, 6, 7, 8 and 9. So, 9 data points I have collected. Now, what I wanted to know, the car was asking that the force acting on it is 2000 Newton and the acceleration we are looking for. Suppose this is the data and now your experiment is no longer into the picture. Now you want to predict what happens at 2000 Newton, how much acceleration is there. So, you can bring mathematics into picture, or you can bring your neural networks into picture, or you can bring your machine learning into picture. Suppose I am bringing machine learning into picture, okay. So, what we will do, we will say that okay, try to fit a linear model. In that case you will get that, you will see that this is the equation. If my acceleration would be equal to minus 1.776 into 10 to the power minus 15 plus 0.005x. How do I get this equation? I have done linear regression. Okay, how we do linear regression, that already is being covered in many other videos. That is not the focus of this current video. So, when we do linear regression or any kind of ML algorithm or deep learning algorithm, we will get some equation, right, or we will get some weights that this is the output, right. Okay. And now if I put x is equal to 2000 here because this is my force, right, call it force, right. So, I will get minus 1.776 into 10 to the power minus 15 plus 0.005 into 2000. So, that is 10 plus minus 1.776 into 10 to the power minus 15. This is negligible. So, I will get my acceleration almost equal to 10 meter per second square. Now, you can see here this is the exact solution I was looking for. So, I am very happy because in a world where I do not know about Newton's second law of motion, I am able to predict my acceleration just after doing some experiments. So, now you see these are the two worlds. One is a world where you have your physical laws, you are using that, and then there is a world where we are using the data to answer your problems. Now, there is a problem. What happens if my data is bad? So, what I am doing here is I am saying suppose at this particular instance and at this particular instance my accelerometer is having some glitch. Suppose this happens and suppose the entry here is 108.75 and the entry here is 558. Entry here is 558. Okay. So, suppose these are two erroneous points in my data set. In that case, what will happen? In that case, if you try to fit a linear model, your equation comes out to be y, which is my acceleration, is equal to 491.0925 minus 0.1923 into force, right. So, this is what you will get if you have these two erroneous points. Here if you put force equal to 2000 now, what will be your acceleration? Acceleration will be 491.0925 minus 0.1923 into 2000. So, that will be 106.4925 meter per second square. So, now you see that this is far away from 10 meter per second square. So, I am doomed here. I do not like this solution because this is wrong. So, it means that the moment your data is bad, you will get nothing meaningful out of this analysis of doing machine learning algorithms or your this deep learning algorithms. So, that is the problem. Now, you look at the title, what happens to our predictions of neural networks or machine learning algorithms when the data is noisy, right. So, your results are wrong. The same thing happens for neural networks as well, right. So, this is the problem that we are going to resolve with physics informed neural networks. So, now if I look at my data, this is not very bad data, only 2 points are there which are causing the problem. So, is there a method which can fix which can fix this kind of problem, right, which can give us accurate results even if there are 1 to faulty points in our data set. So, that is the idea of physics informed neural networks which was introduced in this paper, right. So, this is the paper we will be looking at. So, this was the paper which was introduced in 2019 by Raisi, who is a mathematician, right. So, physics informed neural network, a deep learning framework for solving forward and inverse problems involving nonlinear partial differential equations. So, this is the paper where for the first time physics informed neural networks were introduced, and we will be covering those physics informed neural networks in detail in this series. Please share this video, right, to anybody who is interested in using physics informed neural networks. Thank you for watching. Please subscribe to this channel. Happy learning.